So everyone, welcome to the session about autonomous driving and self-driving cars. So, uh, first of all, good evening to all. So myself, I am Nivin from pantechelearning. So I've been working in Pantech Solutions company for uh, several years, and I have experience in different domains like embedded system, autonomous like systems, robots, and so we are working on self-driving cars research platforms. So today this session will be in introductory sections, uh, session into self-driving and autonomous navigation. So I hope you all are doing well. So we'll just start with the class. So, so first of all, autonomous driving, you all might have some idea about what is autonomous driving and stuff, because we are living in this era where there is numerous new developments are happening. There are so many new systems are there being implemented in area of self-driving. So we have from lowest level to the highest level type of self-driving. Maybe fully autonomous systems are not still not fully available, but there is like systems that can pretty much operate without any human guidance in some selected conditions, but not maybe not in all the conditions. So maybe not in all the conditions, but in some selected conditions. So, so today we'll just see how we can implement. We can implement in the sense this is like an introductory session into. So there we can't do any hands-on right now. So we'll just go through the introductory part of how we can start with the self-driving cars. Like we'll see like different type of open source development platforms and frameworks and middlewares that we can use here, and you can how we can implement it yourself. Like if you're doing research into it, you can even on a hardware level, on an affordable level, how we can make something a system that is very useful for learning purposes and could also help in your in your professional career. So first of all, the idea of what is a self-driving car. So this is obvious to all of you. What is a self-driving car? We don't need to give like a definition. Still, we just see a basic definition. What is a self-driving car? Like in obviously, the definition will be something like a vehicle capable of sensing its environment and moving safely without little or no human input. So a self-driving car could be a vehicle that needs some human intervention, or it could be fully autonomous where there is no need for any human to act on anything. Every scenario will be tackled and handled by the vehicle itself, the system itself. So for that, obviously, it needs to be able to sense the environment. So sensing, the meaning of sensing could it's a broad in the broader sense. It could encapsulate like so many different kind of scenarios where the it could be like vehicles in front of you, it could be like humans or any kind of signboards, could be lane detection or mapping the environment using some mapping sensors, or obstacle detection, or like GPS, using GPS systems. So it could mean so many different things. So you need to integrate all into one system so it can move. So like today's car systems itself, it's a collection of different kind of it doesn't it is like these days if you take a car, it has like thousands of sensors. Even if it is not like some high-end luxurious car, still even if it is a basic model car, still it will have like thousands of sensors to, because it's necessary from engine to cruise control or whatever it is, like dashboard and safety systems. This all needs so many different sensors and so many different type of electronic systems are implemented inside. So these are all combined together. Like we can use CAN network, CAN and LIN network, CAN LIN networks to interconnect all these things and coordinate things and make it work. So today's even the basic vehicles are complicated in itself. They are already complicated, but when we add this new layer like the autonomous navigation layer, it will become so much more complicated, and it has to involve integration of so many different type of areas, like areas of technology. Like it could be computer vision, navigation systems, and like predictive analysis systems. So it has to incorporate so many different areas of technology. So when we talk about self-driving cars, so there is this SEA level of driving automation systems. So there is from level 0 to level 5. There is level 0 to level 5. So level 0 is no automation, human driver, no automation. The system may issue warnings or momentary assistance, example like beeping. So these are like the existing cars, the classical car, which we have available. Most of the consumer cars that are available these days. These are like the type of cars that we have here. Like most of the basic models, like uh, middle variants, they all come with this. They're all this type of no automation. There is no automation system. Issue warnings like it'll give like warning signals, like if there is an obstacle, if there is something behind the car while we're taking reverse, while the car is on reverse gear, it'll give some warning. Or if you're not wearing a seat belt, it'll give a beep sound. So other than that type of systems, it doesn't have any automation. So that type of cars are level 0. Then level 1, driver assistance systems like ADA system, advanced driver assistance systems. These are like available in high-end cars. Even like a decade ago, like luxury cars will provide this type of assistance systems like adaptive cruise control. System can assist with either steering or acceleration, braking, like ABS systems and things like that. They're not intelligent or anything, but they're much better than like the old systems in when it gets to like safety. So human, still the driver is a human. Then level 2, partial automation, home, still human driver. System can control both steering and acceleration brake under some conditions, but driver must monitor and be ready to take over time. To take over anytime. So then there is level 3 system, conditional automation system with fallback to human. System can perform all driving tasks in specific situations. Humans must take over when requested. Example, traffic jam or pilot. So the previous one, the level 2 one, it could be like we can have in luxury cars these days they have like a highway modes where you can just put it in a highway mode, and it will just in straight line, it will move in straight line with a specific speed, and it will give you warnings if there is any problems or anything. You don't have to steer or anything. The vehicle will move on its own. But still the driver is in control, but the driver is in control, but still the system can do some kind of automation on its own. The level 3 system means it can drive in can perform all driving tasks. Like it can perform all tasks like taking turns or detecting pedestrians and other vehicles and map the area. It can do all that, but human must take over when requested. So when requested, the human must like under certain conditions like a traffic jam, the human need to take over. Then level 4 level, so high automation. So the system takes over the entire car. Driving is the system takes over the driving of the car, and fully autonomous, and is defined um, fully fully autonomous in defined areas, geo-fenced. So in defined areas, it is fully autonomous. Humans needed within those areas, but might not handle all road types or conditions. So it might not handle all the road types. Like if we have like certain areas where we have perfectly paved roads and like or lane roads, and there are like dividers and markers like signboards and rails and things like that. If those things are available, are there, then the system it can move. But in certain conditions, like where place where there is no roads, there are no roads to follow. It is just it's just open, and there is no specific road pattern or anything like that. So in that case, it won't be able to navigate on its own. So it's not still not fully autonomous. Like can't it can't drive the car like a human, because humans can look around, and they can assess, and they can easily, like they don't do that in like they can naturally, they are able to judge the surroundings, and they're able to move around, so they are able to drive the car. But with the this type of level 4 system, it is not possible. Then full automation, so the driver is system fully autonomous in all environments and conditions. No steering wheels or pedals needed. Human is not required at any point. So human is not required at all. Even in the first, in the level 4, no human is needed within certain areas. No human is needed, but still a human is needed in some conditions and some places, some roads and some places. So 100% human involvement, like 100% system involvement is not there. But in case of full automation, there is no need for any humans. The car can, like we seen like futuristic movies where the taxi systems, where the person can order a taxi service, and the car will on its own will come to the doorstep. Still there are like some systems are being tested in places like Los Angeles or in Japan. There are some test cases are being done, but it's not like popular or fully developed systems. So that type of system still, like, even if the person wants to go to some faraway place where there might not be, it might be a remote area where the conditions might be different from a city. So even in that case, the car will be able to take the person to that particular place. So that is a fully automated system, where there is no need for any human assistance. The system can fully take over, and it can execute all the different tasks. It can deal with all the different scenarios that might come up. So then we can see each levels one by one, like, and with examples, so we'll understand it more. So first one is level 1. So level 0, obviously I've already told you, like it is like the conventional mid-range type of cars. These are level 0. So then level 1, driver assistance system, where the adaptive cruise control speed only, used in Toyota Corolla, Honda Civic. These cars have this type of adaptive cruise control systems. Then lane keep assistant steers to stay in a lane briefly. So briefly, it will steer to stay in a lane, like Hyundai's Elantra, Ford Focus. These type of cars have this type of this lane assist systems. Then partial automation examples are like Tesla Autopilot is one example of partial automation. GM Super Cruise, Ford Blue Cruise, Mercedes Benz Drive Pilot. level 2 plus in some countries. Then level 3 conditional automation. Uh, Mercedes-Benz Drive Pilot certified level 3 in Germany and some US states. Operates in traffic jam under 60 km per hour. Then Honda Legend Japan only level 3 sedan. It's only available in Japan and it's a level 3 sedan. Then level 4 high automation like Waymo one, that's Google self-driving research project, Google self-driving taxis. So these are available and fully autonomous taxi service in Phoenix, Arizona. So Cruise AV by GM. So General Motors has this car called Cruise AV system called Cruise AV running in a select US cities like San Francisco, driverless rides at night. Then Navia automation shuttle, driverless shuttle buses in private campuses or city zones. So still, even in this level 4, you can see still uh, it is only in certain places, only certain in cities or in city conditions or private campuses or city zones. So these are like limited to certain areas. They're still not implemented fully like in a general in a bigger broader scale. So that's level four. It is automated, fully automated, but in certain only in certain areas. Then level 5 full automation. So no consumer ready examples yet, only in development and test phases. Every like so many companies parallelly are doing research like Tesla and so many other like almost all of the automotive companies are doing research on this same thing. Even IT companies have like research, like IT companies like HCL have like research going on in this type of systems. So so example like theoretical vehicles. So like Tesla is planning this vehicle called Tesla robot taxi. Sook's Amazon fully driverless prototype, and Apple's rumored autonomous cars under development. So there Apple also working on the same thing. So it's a future, so everyone is working on it, but still we don't have a fully automated driver, full automation model, level 5 full automation model yet. So then we'll this is like in general. Up to now we've been talking about in general about the uh, self-driving cars and what is happening right now in that area, like different levels and what is happening and all that. So right now we'll just go into our own Pantech's own self-driving car research platform. So it's an open source scalable lab for automation vehicle experimentation. So it's a experimentation vehicle. You can get it from us, and you can then you can do research on it. You can add more layers to it. You can add more sensors to it. So it uses open source software platforms. So you can develop you can develop the software on your own, and you can add the additional softwares to the existing systems. So the architecture is very scalable for like lab experimentation purposes. So it's an electric vehicle. Uh, so the objective of this lab system, is to establish a modular, cost-effective autonomous vehicle research platform using open source technologies like ROS2 AutoWare to support advanced research in perception, planning, control, and simulation. So the key benefits we have from real-world validation of autonomous algorithms, bridging simulation and deployment, educational impact, and interdisciplinary collaboration, foundation of for long-term AV innovation. So like this system, like I said, it uses open source software like ROS and AutoWare. ROS means a robot operating system. So it's not like a, mm, uh, you know, it won't be like an industrial grade, like high big car, high-end car. It will be an EV, mid-level EV that can like carry like 4 or 5 people, and it will have like certain sensors, and you can use like open source platforms like ROS and AutoWare to develop the software for it. So the advantage of using AutoWare and ROS is that it you can add more and more things onto it. Like if you want to, already provide a number of sensors. Then if you want to add a new set of sensors or a new sensor or some other algorithm you want to try, you can add it easily by by adding the additional packages to the ROS package that we already provide. Then platform overview. So vehicle base, it's an electric drive-by-wire car. So it's a drive-by-wire car. Drive-by-wire means everything is controlled, steering, acceleration, everything is controlled electrically. So the no human normal pedaling systems are not there. It is so you can have like a remote control system where you will be able to control the car, and it's low speed operation. The speed will be low. It won't, though it's when it comes to the automation level, it won't be able to navigate like a level for automated like a high automation vehicle, but will be able to operate in like certain places, and it will be able to move on its own, and it will be able to do many tasks that level 4 level 4 automation car can do, self-driving car can do. Then scalable hardware platform. So hardware platform is scalable. The type of sensors that we can use is, so we will use 2D LiDARs for obstacle detection and SLAM. So the mapping the area, creating a map of the surroundings. For that we can use 2D LiDARs. So we mostly like when it comes to like level 4 or level 3 type of or level 4 type of automation cars, like self-driving cars, it will the type of LiDAR sensor is used is three-dimensional LiDAR sensors. But these are very expensive. Even the most cheapest one would come around like 10 lakhs, uh, 10 lakhs in current market. So that is not very affordable when it comes to research purpose and educational purpose and things like that. So it will be very so instead of that we can use multiple or a single or a multiple 2D LiDARs. So 2D LiDARs means they'll have limitation. It can only map in a plane. It can only create a 2D map, but still it is very effective since we are not since we're not going to be operating this in a very challenging environment, or we're not going to uh, like move with a high speed or anything like that. So because of that, we can easily make use of 2D LiDAR, like a 2D LiDAR system for both obstacle detection and SLAM. So SLAM means so simultaneous localization and mapping. So at the same time, localize the system in the environment in the 2D LiDAR created map, and then again create the map, again improve the map, add on to it. So and then navigation too. So tear for C3 camera, visual object lane detection. So these are very effective, good quality cameras. Those are expensive too, but they are good for like we can use like one or two of these cameras, or if you want to make it like more safe and perfect, you can use like 4 cameras for 4 sides, and we can use it for different purposes, like mainly object detection. So object detection for like pedestrian, that is one important factor in every self-driving system. We need to detect humans or animals or any other kind of obstacle that the behavior need to be different with each obstacle. So like if it is a human, so we need to be more cautious, and we need to be like human or animal, we need to behave in a predictable way, so that it need to detect that type of obstacle. Then other vehicles should be able to detect other vehicles and signboards. And the one of the most important thing, lane detection. So lane detection, you need a camera to detect lanes, so the vehicle can follow the lane and move, uh, move in correct path. So that can be done using this type of cameras. Then GNSS systems, like we can use like GPS systems plus RTK, global localization systems. So GNSS systems, we can use like different type of GNSS or GPS modules to do this. Then IMU for post estimation. So IMU sensors are very useful when it comes to we are like adding more redundancy into the system by adding more this type of post estimation sensors, because in localization we can't just depend on the RPM of the wheels and the 2D LiDAR sensor. We need more data, like to check the orientation, how the vehicle is standing, whether the vehicle is moving or not, is there any acceleration, or it could be just like the wheels could be stuck somewhere and it is just rotating. The vehicle is not actually moving. But if we are just depending on the vehicle RPM, then we'll register that as the vehicle moving. That will produce error. But if we have an IMU system, we can see whether the whether the vehicle is moving. Even the wheel is moving, but even when the wheel is moving, if we can check, we can make sure whether the vehicle is moving or not. So it is to add more redundancy into the like the localization information that we get from the sensors. Then compute units, like we can use NVIDIA Jetson AGX or Savior system. Then ROS 2 will be installed in Ubuntu 22. So we can install like Ubuntu 22 in NVIDIA Jetson board. This Jetson board we can use for all the processing, like all the sensors, cameras, everything can be connected to this single board, or we can connect if we have more, if we need more processing power, we can add multiple boards, or we can use higher variants. So Orin is the lower one and Saver is the higher one. So depending on the kind of software bundle you want to install, you can choose. You can have these two choices. So this system that I'm talking about, the self-driving system, where it will depend on your requirement. You can scale it up as much as you want. You can add more sensors. You can request to add more sensors. We can do it, and we can add more sensors and do it like that. So so all the major like processing will be done on this Jetson board. So it's a NVIDIA board. It has a powerful GPU and a CPU. So these can be utilized for like applications like computer vision applications, where we can run deep learning algorithms. Like we can run high-end, like very high-end deep learning algorithms like YOLO, V7, V8 for like object detection, lane detection, all the different purposes. So then it will be install Ubuntu. We have like latest operating systems in Ubuntu, but still it will be better to install a stable older version, because it will be easier to use. Like most of the ROS packages won't be supported in the new operating system, because the Ubuntu is released, then they have to develop the packages for the new Ubuntu OS. Like the dependencies might change with the new operating system. So it is always better to not always better. It is you need to use an older version. Like if you're using ROS, which is a deprecated like older in robot operating system, there are two versions, ROS 1 and ROS 2. We'll go into robot operating system in a minute. We'll go into robot operating system more in detail. And so there are like two versions are there. Like in Python, there is Python 1 and Python 2, like that. In ROS, there is ROS 1 and ROS 2. So ROS 2 is still active. ROS 1 is already closed. The development has been closed. There is no new developments happening, but still you can use it. If you are already implemented some system using ROS 1, you don't need to you don't need to change it to ROS 2, because it will be so much work but you can still use it, but it will be always recommended if you're making something new, it is always recommended to use ROS 2 because ROS 1 already done. So if you're using ROS 1, you will have to use Ubuntu 20.04 version. So if you're using ROS 2, it is better. It is recommended to currently it is recommended to use Ubuntu 20.22.04. So Ubuntu is the most recommended operating system for ROS, robot operating system. It's very easy to install in Ubuntu. Other operating systems support ROS, but it doesn't fully support like Ubuntu. Then the software stack auto-aware on ROS 2. So the software stack of the particular self-driving system. So here the table is layers, technology, and description. So operating system and middleware. So Ubuntu is the main operating system. And on that, we have installed this ROS 2. So ROS 2 is a middleware. It's called an operating system, robot operating system, but it is not an actual operating system. You need to install ROS packages on. You need to create a ROS workspace and install ROS packages on a existing Linux operating system. So description like communication backbone. So it mainly communication backbone. Like ROS, it's while we implement ROS, it comes with so many different advantages. We'll discuss all that later. So then AV stack, AutoWare universe. For the self-driving part, the self-driving part is built on ROS 2, but it is this particular open source system called AutoWare. So AutoWare is you don't in AutoWare Foundation. AutoWare Foundation is open source module. You can find the source code in GitHub, and you can use it and you can build on it. There are like different levels of the softwares are there, like kind of the depending on how many sensors and modules that you're adding and the kind of vehicle that you're using, you can use this modules, open source modules for localization, perception, planning, control. You don't need to write everything from scratch. You don't need to start from ABCs. You can just study, learn about things like localization, how it works and all that, and then you can implement it using like support packages. These packages that are available in AutoWare. Definitely, you will have to do a lot of programming. Still, you will have to do a lot of programming because it's a general system. It's not for a specific vehicle or anything. You depending on the design, your vehicle design, and the kind of mechanisms that you're using, kind of hardware that you'll be using depending on that, and you might have to add some other customized additional things. So depending on all that, you might have to do so much programming, but still it'll be very much useful and easier than conventional like type of do it from scratch type of systems. Simulations of CARLA, LG, SVL type of simulation systems can be implemented, like this type of high fidelity environment for prototyping. So this type of systems we can easily use for prototyping before going into actual hardware. You can use it for prototyping purposes, like you can simulate your system, your ideas. Then visualization, you can use RVIS, robot visualizer, real-time sensor data, and diagnostics. Then development, Python, C++, Docker, code portability and reproducibility. So then this is the system architecture of our automation system. Sensor input, so there is LiDAR, camera, GNSS, IMU systems. Then it's all integrated with the ROS 2. So ROS 2 uses it for real-time monitoring and logging and actuation of the actuation. Like feedback will come from come directly to ROS 2. Then then the ROS 2 system, AutoWare is actually implemented on top of ROS 2. So AutoWare handles all the other things like, so ROS 2 is mainly used in that case for like communication purpose, linking all the different nodes. So that is the main idea of ROS 2 here. Then all the top on top of ROS, all the perception, localization, planning, control softwares are written in AutoWare. And AutoWare controls the vehicle. The vehicle interface is fully controlled by AutoWare. Then activation is done by it. So then again logging into. So this is the architecture of our system. So robot operating system, software stack overview. So middleware framework, what is robot operating ROS 2? It's a middleware framework for building modular robot applications, enables communication between sensors, compute modules, and actuators used by AutoWare as a core infrastructure. It is a core infrastructure that is used. So it uses AutoWare uses this already existing communication system, like communication between sensors and compute modules and actuators. So this whole thing is done by the idea of creating nodes. So then these nodes have these nodes communicate between each other through this real-time operation DDS based messaging system. So in DDS messaging system, there is a publisher and there is a subscriber and there is a topic. So the publisher can can publish the data. Like for example, you have a sensor node in ROS. You have a sensor node, and the sensor need that sensor data need to be sent to two different places, two different nodes in the same system. So so that in the sensor node doesn't need to know doesn't need to establish communication individually with these two nodes. It doesn't, because that will take time. So the first one has to wait for the second one to finish communication. So that type of communication is very lagging. So what the advantage of this publish subscribe method is that the sensor node will publish the data using a common topic, and the receiver nodes can subscribe to the receiving data, subscribe to the sending publisher using this topic. If they subscribe to this topic, they'll get the data. No matter no matter what, where if the receiver nodes are active, no matter what, whenever the publishes the data, they will get the data. Whatever it is, they'll get the data. Then highly extensible and support wide range of supported packages and tools are available. Seamless integration with simulators like CARLA and RVs. So just take 10 minutes and we'll see a little bit more about robot operating system. So ROS robot operating system. What is ROS like in more extensive definition of ROS, like robot operating system, is an open source robotic middleware suite. Although ROS is not an operating system, but a collection of software frameworks for robot software development. Provides services designed for a heterogeneous computer cluster, such as hardware abstraction, low-level device control, implementation of commonly used functionalities, message passing between process and package management. So these ROS ROS includes all these things. It is not just it's not just one thing. It's a software framework, and it provides services designed for heterogeneous. Like you can using you know using robot operating system, you can interconnect multiple computing devices. It's not you don't it doesn't have to be in a single, like we are in our when we discussed about our EV or self-driving system. I told you, like, we are going to use a Jetson board, or we could use multiple Jetson boards, or even we could add a computer to that. Or so in that case, we can move on and add more computing devices and sensors. There is no limits to that. We can have a cluster of like hardware devices, and this cluster of hardware devices can efficiently intercommunicate and operate very efficiently with the underlying systems, like infrastructure that ROS provides. So then low level device control, like very low level device controlling, like reading like sensor data. Like if you have an I2C sensor, you want to read the data from that, or your encoder motor has a I2C, like a simple pulse interface, where when the motors rotate, the Hall sensors will give you pulses. So where you want to read it using a simple interrupt function, you can use that type of simple functions will be there. And then like from the data is read from this, the raw data is read from these sensors, but the raw data cannot be used directly in software because we need to convert it into a different format. We might not be using the same format. Like we might be getting RPM values. We might be just getting counts like per minute from the Hall sensor. But we can't just directly use that. We need to convert that to some useful, like angle of rotation per minute or per second. That is a useful data. Or angular velocity. That is an angular velocity. So, or you need to calculate linear velocity, like meter per second, from the ticks that we get. So that all that type of conversions, you don't need to write like every single equation for all these conversions. Already everything is that type of small, low level, calculations. Everything is already implemented in ROS. You just have to mention in a configuration file. You just need to mention that this is the radius of my wheel, and this is a wheel width, and this is a wheel base. This is how much distance between my left and right wheels. And by mentioning all these values, it will calculate the necessary things, like by reading the raw data. So that type of interfacing, like low level devices and controlling, is very easy. Like motor control, that type of things have become very easy with the rows. So implementation commonly use functionalities like for navigation, localization, like so this type of systems can be easily implemented, like mapping. Already, these are already implemented in ROS. Message passing. So this is a very important part here, because like I said, it will be a cluster of devices. It won't be like a single system, like a laptop. It will be it could be multiple computing devices, like multiple single board computers or a normal PC, and then there could be multiple microcontrollers, and there could be so many different sensors and actuators. So all these things need to work together. So together means they each are dependent on so much, like dependent on each other. All the devices are dependent on each other. That means there need to be some communication happening between these, uh, you know, between these devices. So that communication, like I said, with using the DDS system, the publish subscribe system, this is made possible, like message passing between processes and things like that. Hardware abstraction. So like hardware abstraction, low level device control, and it is created by this uh, California based Willow Garage, now maintained by open source robotics foundation. So we can't go into like in depth into robot operating system right now. So before ending the session, I'll just give you some demo. So just demo will be just a demonstration of self-driving robots. So this is not a self-driving car demo. This is a self-driving robot, which I can show you the robot. This is our self-driving lab, like self-driving autonomous uh, lab system that we have implemented. So this is like the autonomous mobile robot. So it's a mobile robot. It's not. So there are like we have two levels. So one we have with the robots, like four-wheeled robots, and then another level we have with the like a EV. So here you can learn about automation and self-driving from both the platforms. Whether you're using the cars platform or robot platform, you can learn so much from both the platforms. So this autonomous mobile robot powered by NVIDIA Jetson Nano, so it uses a smaller uh, version. Like in the autonomous car, we have to use like Orin or Savior from the same Jetson series. Here we are using a more basic model like Nano, this Nano support robot operating. It also implemented using robot operating system, and it also uses 2D LiDAR sensor. So this is a car. So it has like a 2D camera, then sorry 3D camera, and there is a 2D LiDAR, and it's a four-wheel car, and the steering, it uses steering drive in using a servo motor, and both the rear end motors are encoder motors, geared DC encoder motors, and there is an IME sensor, and behind here there is Jetson Nano. So this is a platform. You can use it for like learning. You can add more to it. It already has like all these TensorRT, TensorFlow frameworks, Keras, OpenCV already in it. Uses all these things. You can add more to it. So it uses 2D LiDAR for mapping and navigation and mobility steering. It uses this method called Angerman steering, mimics a steering mechanism of cars where the inner and outer wheels, uh, you know, rotate at different angles during a turn. So maneuverability, efficiency in tight turns and curved paths. So it's a very sturdy robot system. It's a fully metal based, so it's very sturdy and rough. You can use it in it will last for very long. Definitely, if you have this, you can implement that like this in a lab system where you can use it for many years. And wheels are very high density solid wheels, rugged chassis fully solid metal for durability. It will last for a long time, allows robot to navigate rugged terrain without suffering damage or ensuring longevity. Pendulum suspension. There is a behind the wheels are not fully fixed. It has a suspension system, high precision pendulum suspension, structure balances the force, enabling good adaptability on to uneven surfaces while preventing any impact on the motor. So it won't like a sudden like collision with any obstacle. It won't impact that much on the motors because it's not fully fixed. It's a pendulum suspension system. Then there is 3D camera for tasks like object detection, segmentation, and things like that. Then AI deep learning and integration. So it uses so many different. So then you can implement this type of a lab setup where you have a small scale self-driving car setup. So this is very much useful because here this uses the same exact type of algorithms and same systems here. Like for example, lane detection, sign detection. Like you can see in this example, detecting crosswalks and signboards, and it can also use the camera and automatic parking. So this is very useful when it comes to learning about self-driving cars like in a very a scaled indoor environment. So this is the system. I can show you a demo of this. So it's not like it's not the same lab setup. It is just our office space. So the car is like initially, initially I can just explain as the video is playing. So this is the RVIS. This is called RVIS, robot visualizer. So this is a visualizer part of robot operating system. Right now, what is happening is the robot using LiDAR sensor, uh, we are we are mapping the environment. So this is a office space. So this is the one floor, and you can see these are like different cubicles here. You can see these cubicles, and there is the door, and here you can see the door, and so it's moving around and building a map. So I'm not even controlling robot. The robot is using you know, automatic moving mechanism. It's or on its own, it's moving. There is no remote control. Nothing's there. But this is not autonomous navigation. Autonomous navigation means we should be able to tell the robot to go where we can just tell the robot where to go. Like I can say, right now I'm just waiting for the robot to map. So there is one more room here. So it need to go there and map it. So once it done with that mapping, I'll just save the map using this command here, rows run map. So that's another thing. Like there are like so many command lines in ROS that are very helpful. That comes in very handy when it comes to this type of operations. Like I'm going to save the map right now. The map is I have all the play areas mapped, and other than this small portion here. So I'll just save the map. So right now it knows that it didn't go to this place. So it just the path automatically there is a path created. So it is going there to map that unmapped area. So it is just exploring right now, exploring the areas. So right now I just press enter. So it saved the map. So then I'm just going to run autonomous navigation right now. So I'll just copy paste the map. I'll just right now it's launch. Right now I'm launching the autonomous navigation. So slam here. So that is an actual robot that you're seeing in the RV's visualizer. I can show you the real video. In a minute, I'll show you the real video. So this is the visualizer. It's showing an actual robot and the environment that we just mapped. Right now, I'm just giving the destination. So I want the robot to move to this location. So it starts moving. So this is a velocity vector, this thing that is moving around. This is a velocity vector. So it is showing which direction to go. So it will always stick with the edge because it want to follow the shortest path. So it can move around and there is so much space here, but still it's sticking with sticking to the edge because it always want to follow the shortest path. So right now there is small problem there, so it's taking reverse. It's a very congested space, so that's why it's not able to. There is a judgment problem there, so it went too far, so it took reverse. Then now it is just going in the right way. So it'll just do what I said to do. Like it'll just go, and so that's a room. So that's a separate room. So it is entering that room through the row door. All the black is the black part is the uh, walls, and the white is the free space. And that blue this is an inflation map. It's the local map, global map, and this is the local map. Local map only maps the immediate surroundings. It's not concerned with like all the surroundings. It only maps the immediate surroundings with an inflation layer. Inflation layer means this is to avoid collision. There is nothing here in this red part, but the robot will not, and nothing here in the red part, and also this part, this blue part, there is nothing, but still the robot will try to avoid this because it will try to avoid any collision. So I can just show you the real video of the same thing. So this is the real video of the same thing. the same place that we saw in that visualizer. Everything is sticking to the edge. So all the black space that we saw was this cubicles and stairs. Right now you can see that it is move forward a little farther and it won't be able to turn completely. But there is nothing there. Still it won't. There is nothing there. Like it can easily make the turn, but still because of the inflation layer that I added, it is not going to go too much close to the wall. To avoid collision, we just add that type of things. So it will always keep some distance from the being the primary cover. If there is no space, just if very well, so it's taking the time. You can see it's going level, going to stick to the other side of the wall. It always is the shortest path. So, and now we just go right click. So it's the second one. There is no operation. So adjust so I'll just give you like controller's location. So we'll start here. It reaches the location. So that's the demo output of the system. So this is here this system this is like an example of robot operating system, like what we are doing here. So this is I've installed Ubuntu. This is Ubuntu installed Ubuntu 20 version installed 22 version installed here. It's not so it isn't not exactly Ubuntu. It is like yeah, Ubuntu version installed that supports Jetson Nano, and all the packages, everything is installed in the Jetson Nano itself. So this is the visualizer is called RVIS visualizer. You can have like we have different options for debugging, for you can see errors and any kind of problems. If something is not properly connected or attached, then you can see those type of error messages here. So that's it. This is what we can cover about robot operating system and automation in this session. So thank you everyone. Thank you for giving me this opportunity. So I hope this was helpful for you. So you can use this as like a like a first step, and you can use this knowledge to gain more practical knowledge into this. There was no hands-on. I was just explaining terms and I was just showing you demo videos and things like that. But you have captured like so many. You might have already known some or most of the things that I said. But if some of you haven't uh, heard of these things before, you can use these keywords and you can use these ideas to get more into this area, and you can learn more. Like all these things are that I've talked about, all these are open source. So you just have to make a small robot setup and buy some hardware parts. It costs some money, but you'll be able to learn so much from this. So thank you everyone. So we'll just wind up the session for today.